All right, so let's get back. So as I mentioned in this part, and I know it's getting a bit late, so I'll try to keep it short. This one I will show a lot of equations, but I'll try to highlight these main points of them. And the main goal would be to, now that we understand what this machine is and how useful it could be, how do we actually go ahead and build it? Okay? And as I mentioned, there are several architectures, several platforms, material platforms that people are looking at, and no clear winner at the point. Like there's no CMOS yet in this community, and with each platform has its own advantage and disadvantage. And you'll hear in the school also about few other platforms, like Mahesh probably will talk about spin-based systems. So I will focus on this so-called superconducting material-based platform, which is again one of the leading platforms in terms of where it has reached today. Because of a lot of involvement from tech giants like IBM, Google, they are focusing on this particular platform. Okay, and what I'll do is I'll talk. So there are many aspects of it. How do you fabricate this? How do you engineer, communicate, and all that aspects of it, which I will not be focusing on. What my focus would be on a basic: how will you build qubits? How can you build qubits out of superconducting platforms? Okay, how can we define qubits? Then how do we manipulate such qubits, and how do we measure such qubits, and what are the challenges? Okay, so those are the main aspects, one fundamental aspects that I will try to focus on this particular talk on. Okay, all right. This is just a picture from one of the IBMs, okay, and I'll try to explain all these, basically how these forms a qubit and how do you communicate with them. Okay, and these are kind of things that you can right now access. You can convert your laptops into quantum computers because these machines are available in the cloud, so you can send signals and perform quantum manipulations on such qubits and read out those patterns of probability numbers. Okay, there are codes. There's several languages like Qiskit or Q-sharp where you can use them to actually do this manipulation. Okay? But again, we'll not be focusing on those aspects of things. I'll be happy to chat with you a little bit on how that's done if you're interested in that aspect. Okay, all right. So now the slides will be very busy, and I apologize for that, but I'll walk through each one of them. Okay? So the basic idea, the first thing that we want to do is how do we define qubits in superconducting? Okay? And the starting point of all this is the idea of quantum harmonic oscillators. Okay? So this is something that again I assume that you have already heard about. Srijit also mentioned about quantum harmonic oscillators. So I assume that everyone knows that. Okay? So the basic idea is if I take an LC circuit. Okay, this is an electronic way of creating a harmonic oscillator, because if you write down the energy, now I'm thinking about classical domain yet. So if I combine L and C circuit together, then the total energy that's stored in this material can be thought of as the magnetic energy stored in the inductor and the electrical energy stored in the capacitor. Okay. And each one of them can be written down. Where if there's some charge Q on the capacitor plate, that energy is Q squared by 2C. If there's some flux phi thread through this inductor, then that energy is phi squared by 2L, okay, where L is just the inductance of this coil that you design, and capacitance is the capacitance of that particular plate that you design. Okay. Now the whole idea is this energy looks awfully similar to a spring mass system or any harmonic oscillator, particularly in a parabolic potential. If we make the final, we can make the final analogies, where let's say charge can be thought of as position-like variable, and flux can be thought of as a momentum-like variable. Okay? So if I make that identification, Q is like X and phi is like P, then this is also like half kx squared plus p squared by 2m, where capacitors and inductors becomes mass and the spring constants. Right? So if we make that analogy, then the dynamics of the systems really maps onto that of a harmonic oscillator. In some sense, it essentially says that if I have generated some finite Q, let's have finite, if I take a spring mass system and dislocate it from its equilibrium position, I can put some finite charge, and what will happen is this charge will start producing current through that inductor, okay, and this electric energy will be converted into magnetic energy, but then this energy this magnetic energy is not in its lowest energy form because it's phi squared by 2L. If there's some flux phi, then it will start to lose this energy and give it back to this charge, and you keep on oscillating the energy between the two. It's exactly same as the harmonic oscillator. Right? So then this LC circuit is like a harmonic oscillator. Right? That's the first message. Then when you can think about going into the quantum domain, let's say, and I'll make this more precise. Let's say if I can make a quantum LC circuit, let's say operate this circuit in the quantum domain, then this will become like a quantum harmonic oscillator. Okay, and for that I need to lower temperature and do things which I'll talk about. But let's say if we can go in the quantum domain, operate that same circuit in the quantum domain, then the states of this are now labeled by how many quanta of energy is stored in this oscillator, right? Just like in the quantum harmonic oscillator, I have the quanta of the oscillations gets quantized. Here, the electromagnetic oscillations gets quantized, which is called a photon. Okay, so how many number of photons are stored in this circuit labels the state now. Okay, and they come in discrete quantas, which are all equally energy spaced. Okay, where the energy difference is just h bar omega c, where omega c is in this case the frequency of this oscillation, which is given by L and C. So that's something that you can design in lab. Okay, by designing a particular inductor and capacitor, you can design this gap. It turns out that typically these frequencies come in the gigahertz domain. Okay, so this is a microwave photon. Okay? Based on the sizes of these structures that you can design, the values of inductors, capacitors that you can design, this frequency comes out to be gigahertz. Again, an important number to remember. Yeah, question. Sorry?
Do we actually see photons?
Well, what do you mean by see? Right? You can measure things, whatever you can measure in labs. You can. People have done measurements of measuring single photons in the system.
In these LCs.
Yeah. Right. Okay. All right. So that the mathematically what that means is I need to promote q and phi to operators now. They're no longer classical variables. Okay. So then, and in a particular state, actually I cannot tell you what phi and what q. In one of the eigenstates of the system, I cannot tell you how much charge is there. They fluctuate. They keep on fluctuating because it's not a variable which commutes with the Hamiltonian. Just like in a quantum harmonic oscillator, the position keeps on fluctuating, the momentum keeps on fluctuating. Same thing here. If I go in the quantum domain, I see charge fluctuations, and that's how people tend to measure these circuits also. Right? Okay, good. So, so that's the Hamiltonian that will become. It's just rewritten over here in renormalized by introducing new variables. You sort of normalize charge with 2e. The reason for 2 will become clear because we'll be using superconductors to make this. So that's really a Cooper pair that needs to be used. So this twice the charge. If you normalize this, define this variable, and similarly normalize this flux with the flux quantum that was discussed in the morning. So then you can convert them into dimensionless numbers. So this is a nice dimensionless form. This is energy units. So think of this as like I'm specifying capacitor in just energy units. And what fundamental constant I need to convert that, that's what this number is. And here I'm specifying inductors in the energy units by using flux quantum as the variable. Okay? So it's a nicer form which you'll see most of the time written down. This is called the charging energy. This is called the inductor energy. This is the capacitive energy. All right? And this Hamiltonian can, rather than working in this n and phi language, as we do for quantum harmonic oscillator, we shift to this creation and annihilation operator language. So you can kind of like factorize this, n plus I phi, n minus I phi kind of thing, right? You define your new variables, a and a dagger. And the same thing can be written down this, and here's again, if you do this properly, that's what, so it's phi plus in, phi plus in, phi minus in are these a and a dagger operators. And the reason why you want to work with this is just much more simpler to work in this language, where you can think of now these as creators and annihilations of this electromagnetic quanta in this harmonic oscillator, right? So that's what the mathematical description of the circuit would be if we can go into the quantum domain. And now the idea is, hopefully we can utilize this discrete 2 levels as my 2 levels for the qubits that we wanted to construct. Okay? So that's how we use LC circuit, I can think of it. And the nice advantage these circuits bring in is these are like charges and flux. These are things which I know how to manipulate. Okay? So I can apply voltages to control the charges in this circuit. I can apply flux via current lines to control flux in these circuits. So they give very nice controllability, these type of circuits. Yeah.
Classical LC circuit, do we actually see light coming off?
Light coming off?
Yeah, like here we have photons.
Right. What I mean is that there's a microwave photon that lives in this oscillator, right? It's kind of, it keeps on oscillating. Of course, these fluctuations will also generate some radiation. Depending on the strength of it, you can see those radiations or not. Right? What I mean by the state of this is now a particular state of this is stored in an oscillation that's happening here. Okay? How many such quanta of those oscillations in terms of h bar omega is there? That specifies the state of this system. Okay? It's an eigenstate, so it will be remain in that particular state, unless of course you interact with it. Okay, so now let's turn to this question of when can we observe this? So the circuits that we operate today, we don't see them being in this quantized behavior. We don't observe such quantized behavior in the systems. So the reason for all that is, first of all, to see this such quantized behavior, if let's say such circuits are operating in a regime where it's occupied by tens, hundreds of thousands of such quanta of energy, right? Let's say 10 power 5 h bar omega energy stored in the system, it's in that state. So if it's 10 power 5 or 10 power 5 plus 1, it does not make much difference. Okay? So I will not be able to distinguish between the two very well. And hence, the first condition I need is this should be operated in the so-called near single quanta or few quanta regimes. Okay? What makes such states occupied? First of all, temperature is very important, because thermally it can be just populated by thermal fluctuations. So if an energy scale which we take for temperature kT is much greater than these gaps that are appearing there, they will just thermally populate it and you'll get a sort of like continuum behavior. You don't see this discrete nature. So the first condition needed is your temperatures must be much smaller than these gaps. Okay? And these gaps are gigahertz frequencies for typical microwave circuits. That already puts this temperature in few millikelvin. So I think 1 gigahertz is about 100 millikelvin of that range. So you need to be at least an order smaller than that. And so that's why it puts you to some 10 millikelvins. Then such discrete nature starts becoming important. Okay? Another very important point is that these levels, the energies are, these systems are also interacting with the environment, right? So all talked about LC, but there's also a resistive part, R part of the circuit. Typically, if you make any circuit, there will be LCR. R says it's interaction with some dissipation in the system. Okay. In that case, the energy is not really well defined. Depending on the state of the environment, the energy can wobble. Okay. So the resistance, essentially what it does, this energy gets broadened whenever there is dissipation. Think like if you're doing a LC circuit, some resonance experiment, it will peak at some resonance frequency, but that peak is usually broadened because of resistance in the circuit. Okay. So then, as a result, these are not really well sharp defined objects. If there is resistance, dissipation in the system, they are broadened. And how much broadening happens, that depends on the dissipation value. Right? So you also want this broadening should not be of the order of the gap. Otherwise, this state will also start behaving like continuum. Okay? You don't get this discrete nature. And as a result, you want to kill dissipation as much as possible. Superconductor allows you to do that precisely, right? Because if you make superconducting materials, they conduct without the resistive part. Okay? So if I construct a superconducting LC circuit, operate it in millikelvin regime, I will satisfy both of these criteria, and this circuit starts behaving like a quantum harmonic oscillator. That is the reason why these lines are built with superconductors, and they are cooled by dilution fridges to this sort of millikelvin temperature range when you start observing this quantum behavior of these circuits. All right? So that's the first important point. Any questions on this? That's fine. Okay, so then what we have learned is if I make an LC circuit out of superconductors, cool it to millikelvin temperature, I can generate this discrete. I can create in a lab a circuit which behaves like a quantum harmonic oscillator, can be controlled by electrical degrees of freedom, which we know very well to do from all this electrical machines that we have so far. Okay? So that's the whole advantage of this machine. But there's still one problem if I try to operate just this naive circuit as a quantum, as a qubit. The reason for that is we know for harmonic oscillator the energy level spacing is all equidistant. Okay? Now for qubit, I want to restrict the dynamics to 2 levels of the system, right? It should be 0, 1, combination of those 2 numbers. If I come in, let's say, with some external drive, let's say an electrical drive which couples with the system and tries to drive the system out, and if I tune the frequency to match this, then I can cause transition between 0 and 1. Okay? So I can start to manipulate the system. But there's a problem with that, because if it can the same drive which can cause transition between 0 and 1 will also cause transition between 1 and 2. And so on and so forth. So it's not a finite dimensional 2-level system. It is actually, the dynamics will happen in this large space. Okay? So how can I restrict it? The way to do that, why the energies are equally spaced, it comes from the harmonic part of the oscillator. It's a parabolic potential. That gives rise to this. There's just one frequency component in the system. Okay? So that single frequency, meaning there's only one frequency scale in this whole system. There's just one frequency, and that's why the spacing is all same. But if I make my system anharmonic, okay, the parabolic potential, let's say the amplitude that I'm giving of this deviation, the energy the frequency depends on that system. Okay, so it's not just one frequency in the system; it's a non-linear anharmonic potential. Then there's hope to make this energy levels unequal. Okay, And that is, if we can bring in such anharmonicity in such circuits, then I can think of focusing on just two levels and only communicating it with external drives which are focused on these two levels, and then behaves like a qubit. Okay? So introducing anharmonicity is a very important key ingredient, and the fact that allows people to do that was the discovery of Josephson junction. Okay? So that's what we come to next. Okay. So Josephson junction. So Josephson, I here as a graduate student discovered this particular phenomena, and in fact what he was looking at was, so we know that superconductors can carry current without dissipation. What he was looking at is, if I take two superconductors separated by some barrier in between, let's say which is not superconducting or weak superconductor, can I still get tunneling of these electrons and get dissipation, less electron flow in this? What is the IV characteristics of this? If I apply some voltage, how much current can you get? What is tunneling happening? That's were the questions that were motivating him, and he famously derived these two relations, which I think the best resource to understand these equations are in Feynman lectures. He gives a very nice sort of cute derivation of these equations, where essentially you can think of as solving a quantum mechanical problem with Schrodinger equation, seeing how these superconductors dynamics happens. And what he derived, again, we'll not go into all that. I'll be again happy to chat about it. But the main thing that he derived was the following: that he says, if I view this as a black box, the amount of current that goes in for a given voltage is derived by these two equations. The first equation tells me that the current that flows in this is governed by some constant I0, which is a property of the junction. What is the size, how close these two superconductors are, and things like that. How much overlap you can get between these two superconductors for tunneling purposes. That governs this number times sine of phi. Okay? Where this phi over here is an interesting quantity. It is the phase difference between the phases of the two superconductors. Now, I also assume you know a little bit about superconductors. A state of superconductor is specified by all these electrons sort of pair up, and they all fall into a particular wave function. Okay? And that wave function is characterized by a phase. Okay? So that phase, again, it's not an observable. Phase is not an observable, but the difference of those phases will again becomes all observable. So if I take two superconductors, the difference of the phases becomes an observable. In fact, it governs the current in this particular case. That's what the main result, one of the main results that Josephson derived. Okay? So current is given by a quantity, again, governed by whoever made that junction times sine of this phase difference of the wave function on the two sides of the superconductors. All right? So that's first quantity. And then how does this phase evolve? Well, the dynamics of this phase is governed by the voltage. So what phi dot is given by QV by h bar. So these are fundamental constants. Given the particular voltage that you apply here, the phase phi will keep on evolving. In fact, what this says is there's a solution of these equations when phi dot is 0, okay, that is no voltage, but there's some finite phi value is possible, and there's a current keep on flowing in the system. So there's a dissipation flow of tunneling of these Cooper pairs. It supports dissipation less flow of the currents in absence of voltage. So there's no dissipation in that particular case. All right? But that can only happen up to a particular critical current. If you keep on trying to crank up the current and try to force current bigger than this value I0, then in that case phi starts becoming a dynamic quantity and you generate a voltage in the system. Okay? So it has some very interesting dynamics, this particular system, but those two relations are famously known as the Josephson relation, written somewhere in the appendix of his thesis actually, for which he was given the Nobel Prize. Okay. All right, so these are very famous Josephson relationships which governs the IV characteristic. For our purposes, one very important property of this, you can think of an analogy of this. What happens is, let's say if I try to build some current in this circuit over here. Right? The way, if I start building up current, that starts building up phase phi, difference between the two things. Okay? This is kind of like an inductor. You start to run some current through it, you build some flux. So the reason it's written as phi is not serendipitous, it's actually for making this analogy a little bit more concrete. What happens is, if you start to run some current, it builds some flux. In this case, it's not really flux, it is a phase difference in the two-way function. But as you start building this I, you start building this phi. Okay? Now, if phi changes, that change in phi generates an EMF, generates a voltage. Just like in an inductor, if you start to run thread some flux, you start generating voltage. Okay? You have to work against that voltage to build to a particular current. That work gets stored as a magnetic energy in the inductor. Here, again, it gets stored as an energy in the system. Okay? And phi really behaves exactly like the flux in inductor, right? With one key difference. If I want to define, let's say, an inductance in this case, which is d phi by di, right? If I want to do that, I can differentiate this equation. The inductance depends on the value of phi itself. Okay? So it's a non-linear inductor, okay, where the inductance depends on the value of phi. And that non-linearity is critical because now, just like how you calculate half Li phi square by 2L, the energy stored in the inductor, you can do same calculation here, but with the fact that inductance is non-linear, it depends on the phi. So I need to perform an integration with keeping the L inside the integral. Okay? And do that integral over there. The energy that you'll get now is no longer phi square, right? It becomes cosine phi. It behaves like cosine of phi. This is an harmonic value of potential. It's not phi square. It's cosine phi. And that is the key advantage this circuit brings in. Okay? It behaves like an inductor. So this is Joseph's junction in simple sense is a non-linear inductor which does not dissipate energy. Okay? So as a result of that, I can use this replace my LC circuit that we were talking about. We can replace this L part with a Josephson junction and get my anharmonic potential. Right? And now if you calculate the energies of this combined system with the cosine phi energy in it rather than phi square, you will get an unequal spacing in the circuit, and those two levels you can exploit for building a qubit out of it. Okay. All right. Any questions on this part? Oh yeah, capacitor, right. So you just replace this for the L part of it. This naturally also has a built-in capacitance because there's just two superconducting plates separated by some insulator. So there's a capacitance associated with it. But what usually you do is you actually do a parallel capacitor. You can add a parallel capacitor. So capacitor is tunable by adding some extra additional capacitor to it. And in fact, what the circuit that we'll talk about is we would like to actually make this capacitance capacitance small by adding additional capacitance to it. Hey, wait, did I say large or small? So if we want to build a large parallel capacitor, okay, and we'll add a parallel capacitor with large value, and the reason will become clear in a bit. Okay? But you can add additional capacitances to it. Okay? All right. So we are actually just coming to that particular. Okay, so now my Hamiltonian of the system, or energy in the classical domain, but in the quantum domain, the Hamiltonian of the system has the usual piece, which is q square by 2c. Plus, now there's this Josephson energy, what people call as the Josephson energy. That's the energy stored in the twist of this phase phi. That comes as Ej cosine phi. Okay? And we would like to use this now, as we already pointed out, this will give rise to unequal levels, and then use that two of these levels as a qubit. That's how all these designs in IBM and Google's machine is what each qubit is built up of. Okay? And there's one more important point here is there are several choices of EC and EJ you can make to design your qubit. Okay? What you want to optimize it for is the following things. First, you want as large anharmonicity as possible, right? Because if they are as close to being a harmonic potential, it becomes as far away from the qubit. Okay? So you want to optimize for anharmonicity. Right? There's another important thing. You want to optimize it for being as least sensitive to charge as possible. Because it turns out it's really this charge noise. These are electronic systems. It's really charge fluctuations that dominate the noise sources in the system. So anytime the charge fluctuates, it will couple to your qubit, which is something that you don't want in the system. Okay? Because those are sources of errors that you want to avoid. All right? So you want sensitivity to charge to be minimum. Okay? So now if I stare at this equation a little bit, so this is q squared. That's the charge part of the energy. Okay? So if I were to, let's say, make EC very, very small, what will it do? Well, the charging part, if I want to draw a parabola, let's say energy as a function of, let's say, charge that is there in the system, the curvature of this is controlled by this EC term. Okay? If I can make this very, very flat, right? This curvature very, very flat, then the energy change, if I have charge fluctuates, is very tiny in the system. Okay? So it becomes less and less sensitive to charge if this was a very flat parabola. Okay? And that is what one wants to do in order to operate this qubit as, and the main thing that governs where you want to operate this qubit is depend on this ratio of this EJ versus EC. Okay? If EJ over EC is very, very small, or in other words, let's say EJ dominates in this energy term, if EJ dominates, then the energy of this will rise very quickly with phi. Okay? So the fluctuations in phi will be very, very tiny in that particular case. Okay? Let me see. Did I do it wrong? Yeah. If EJ is very, very tiny, if EJ is very tiny, then it's very flat. This part becomes, I need to change phi by a lot to change the energy by 1 quanta. Okay? So let's say if I put in 1 quanta in this circuit, h bar omega, single quanta, if EJ is very tiny, that means the fluctuations in phi will be is very large in that particular case because the parabola is very flat, right? So if the fluctuation in phi is very, very large, phi does not become a very well-defined quantity in this circuit. Phi is fluctuating very, very rapidly for a single quanta. But charge, if this ratio is very small, the charge is EC is very large, so that's a very skinny parabola in charge degrees of freedom. So then for the same energy, charge cannot change much. Does this make sense? Right? So if charge cannot change much, then charge becomes a well-defined observable in the system. The fluctuation in charge is tiny, but fluctuation in flux is large. And then that regime is called, this behaves like a charge qubit. Okay? In the opposite regime, when it's very, very large, then this behaves like a phase qubit because phase becomes it's called a phase qubit because phase becomes very well defined, but charge fluctuates wildly. Okay? So in these, charge qubits tends to be more sensitive to charges because quantum mechanical fluctuations are very tiny in charge. So any environment fluctuations which can surpass the charge fluctuations in the system. And as a result, it becomes very sensitive to charge noise, this particular system. So you want actually not to be in this limit to make it less charge sensitive. In fact, it turns out that there was a seminal work which showed that how does this sensitivity, how sensitive is to this ratio. It turns out that it's exponential sensitive in this particular ratio, but anharmonicity is almost algebraic in this ratio. So what happens is you want to make this ratio as big as possible to avoid sensitivity to charges, but you cannot make it arbitrarily big because that means EC will become very, very small and you lose the anharmonicity at some point. Okay? So what they've calculated is as a function of EJ over EC, how does this both anharmonicity and the sensitivity to environment changes? And what they observed was that in this particular regime, about 50 to 100, when this ratio is about 50 to 100, that's when you get enough harmonicity. By enough, I mean the separation between the two levels over there. The anharmonicity is of the order of the gap. Okay, so you can build this as a two-level system. And at the same time, it's very less sensitive. The charge noise is suppressed a lot in the system. That particular design got the name of transmons. Okay? So here it was charge qubit, here it's called phase qubit, here it's called a transmon. Okay? And that transmon really revolutionized the community for using superconductors as, because otherwise charge noise was killing everything and the anharmonicity was not that large. Okay? So with this discovery, people started designing these qubits, which are called transmons. Okay? So we will focus mostly on transmons as an example, and this is really the qubit that's used in current IBM and Google architectures. Okay. So the main thing then, how can you go in this transmon regime is, as an answer to your question, you can add a capacitor in addition to this qubit, and that capacitance can control EC. Okay, so then you can control this ratio of EJ over EC such that the fluctuations in phi becomes tiny in this particular case. Okay? So in that regime, when EJ over EC is large, about 50 or 100, you can see that this as a perturbation. This particular term is this is small. So then cosine phi you can expand in terms of powers of phi, and as a result of that, well, the first term is just a constant, which is just a reference you can throw out that. The second term is the parabolic part of the potential. And this is the leading order non-parabolicity that is introduced. Okay? So you can restrict your Hamiltonian to this. That becomes the Hamiltonian of transmon qubits. Okay? So as long as you are in this ratio, you can make this approximation, and that describes basically a transmon qubit in this particular case. All right. And then this just becomes a perturbation. This part is which you have already seen. You can define an A and A dagger. This is the usual harmonic oscillator. And this is the leading order correction. So you can apply perturbation theory gadgets to calculate the energy levels and what would happen if I try to come up with some external drives and things like that by operating with this particular Hamiltonian. All right? Okay. All right. And in fact, you can use this to calculate what is the leading order anharmonicity that you generate in this system. What determines that? And in fact, to do that, what you can do is in this, starting from this, you can define your A and A dagger operators, which is just n plus I phi, n minus I phi, those kinds, right? You can factorize this part. And for phi, you can substitute A plus A dagger. Right? If you add this A and A dagger, that's like phi variable. And so this term becomes just A plus A dagger to the power 4. There's normalization constants. If you plug in all the normalization constants, this term is completely governed by the charging and EC part. Okay? So this is really saying that it's the charge, the EC part of the energy, which governs how much anharmonicity that there is in this circuit. Okay, that's present in this circuit. Okay. So here's sort of the main result that I wanted to highlight, comparing the usual quantum harmonic oscillator that you're familiar with, where again I have defined this variable n. Yeah. This particular term, right? So this is more like let me actually try to show this. In the first order perturbation theory, it does not. It just in the to leading order, it just shifts the energy levels. Yeah, right. That we can calculate actually by perturbation theory. Yeah. In fact, you can use perturbation theory to. So you can see that this will be some fourth order in A. And that's like 2n operator. The n operator is A dagger A. Okay, so then you can define an A dagger A is same as the n operators. You can translate this term into the operators, which goes like n, and then you can immediately see what it does to the energy levels. It just shifts the energy levels in this case, right? And the main thing is that the shifting is different for the level I'm talking about. It shifts differently, and that gives the anharmonicity. No problem. Yeah. Yes, sir. Question. Oh, yeah, so the way it happens, sorry, I'm being a bit fast here, sloppy here. So the way it does is, again, the starting point is you can start from this up to this, that's clear, right? So you just restrict it to that phi term. Then what is phi? I can write them in terms of A and A dagger, okay, which is A plus A dagger, but there are these normalization constants. Phi ZPF, right? And I've written down that normalization constant down. You substitute all of this, you see that EJ will completely cancel by, so there's EJ 1 power 1/4, there's a fourth power that comes and that EJ gets cancelled. So to leading order, and how much is completely governed by this EC term, just the EC term. Right. Okay, so again, using perturbation theory, you can write down the Hamiltonian up to this leading order, and its only effect is to shift the levels of each of these energy levels, and that shift depends on which level I'm talking about. So this n operator is just 0 for the lowest level, 1 for the higher level, 2 for the next high level, and so on and so forth. Okay? So then, for example, you can see the 0th level, this does nothing to that 0th level. To the first level also, it does nothing. Okay, so the lowest two energy level gap is same, omega c. But it starts kicking in at the n equal to 2 value, okay? And it shifts that energy by this much amount. You just substitute n equal to 2 over here, so it just shifts by EC, that particular number. Okay, so the picture is, in the quantum harmonic oscillator, everything is just equally spaced. In this transmon limit of this, you get unequal, so bottom two levels remains unshifted, but then the second level gets shifted just by EC. Extra small EC correction you get. So then the anharmonicity is really just governed by this value EC. Okay. Now you EC can't be made negative, yeah. Right. So now you can operate on the bottom two levels, and then come in with a drive which is just resonant with these two and make it behave like a two-level system. All right. So that's how the transmon qubit operates. And this is exactly these qubits that are drawn here are nothing but shunted capacitance, large capacitance shunted Josephson junctions, okay, operated in millikelvin. That's exactly these things over there. Okay, let's see how much. Okay, I have about 6 minutes, so I'll probably speed up a little. Probably not go into details of the calculation, but highlight the main points of each one of them. Right? So that's the first part. How do we define qubit? I hope that's clear. That it's essentially just a shunted capacitor Josephson junction. Okay? And the reason for doing that is to make it less sensitive to charge noise. Okay. Now the next question comes is, how do I manipulate qubits? And in manipulation, as I've already pointed out, we have, if I can do single qubit and a 2-qubit gate, then I'm done, right? So we can construct a universal computer based on that. So how do one do single qubit operation, and how does one do this 2-qubit entangling gate can generate? So here, just again a quick reminder of 2-level systems. How 2-level systems are manipulated is by this idea of Rabi driving of the system, right? So where if you have 2 levels, you come in with a field which is transverse to the quantization axis and oscillating at a frequency governed by the gap, the difference of the two. If it's resonant with that particular thing, you can cause transitions between the 2 levels. And then just by timing the pulses, this is something well known in the NMR community, you can design your pulse such that you can be in 0 state or 1 state and perform these sort of gate operations, single qubit rotations. Okay. Just so the main result that was well known in the community was that if I come with this transverse drive, so this is the Hamiltonian, effective Hamiltonian of my 2-level system, which will have reference to some middle energy. So if it's in state 1, then it has an energy minus h bar q, that's this one. And if it's other state, it has energy plus h bar omega by q. So it's just a qubit sitting in the lab can be written down as this 2-level system, right? And then I come with a field which is transverse. Okay, so it has sigma x and sigma y components. So that's why it will have off-diagonal elements, and this will cause transitions between the 2 levels. Okay, so that's the drive I can come up with. And the 3 parameters, main parameters of the drive one controls is the amplitude of the drive, the frequency of the drive, and the phase of the drive. Each of these 3 parameters controls 3 separate things of what dynamics happens on this block sphere. The amplitude of the drive, if I am resonant, if this frequency matches the qubit, then amplitude governs how fast rotations are happening on this qubit. Okay? That's the so-called Rabi oscillations, how fast this qubit. So then if I control this, I know how fast 0 will be, for example, going to 1, and 1 will go into 0. So hence, I can time it appropriately so that if I want to convert 0 to 1 or stop somewhere in between, apply all these so-called pi by 2 and pi pulses on this qubit and make it go in some different state. Okay? Frequency just controls that if I have resonant, then I'm causing this transition. So for us, this is very important because of this anharmonicity. This can effectively carve out this 2-level system by choosing the frequency to be between the lowest 2. I can just do manipulations in this lowest 2 subspace and create a qubit out of this whole system. This governs how much rotations are happening. The phase governs which axis about which the rotations happen. So this qubit can be rotated from about the x-axis or about the y-axis, and so on and so forth. The phase of the drive can be used to govern along which axis this happens. Okay, so hence, by controlling these 3 numbers, A, you can create a qubit out of this anharmonic levels, and B, you can actually do arbitrary single qubit rotations in this. Okay, so then a transverse drive is what is needed to cause these transitions. Okay, so what creates this transverse drive in this superconducting architecture? So how to apply this transverse drive? For that, again, we notice one thing. The thing that we have already done, these A and A dagger operators were like phi plus n and phi minus n. All right? And A and A dagger operators, if I write down in their full matrix form, this you know from quantum harmonic oscillator, they look something like this. But if this A and A dagger operator, I'm only restricting my dynamics to this lowest 2 subspace, they contain this off-diagonal element. Right? In fact, A plus A dagger, if I look at it, it has only elements in the off-diagonal part of thing. Okay? But A plus A dagger, if you follow the definitions that we did, is nothing but just like behaves like phi and n. A plus A dagger behaves like one, and A minus A dagger behave like the other. Okay? So the operators phi and n, which are nothing but fluxes and charges, behaves exactly like transverse in my 2-level system, for my 2-level system. Okay? So if I can create an oscillatory charge on my plate of the capacitor, that behaves like an oscillator field applied for my 2-level systems. Okay? All right, so that is how we will be creating. So basically, charge will behave like a sigma x field, and flux will behave like a sigma y field for my this qubit in this case. Okay? And that can be controlled. We can apply a drive like this, just by a simple electrical circuit of the following form. So for example, if I want to control the charge at this node for my LC oscillator, all I have to do is to couple it to my external drive, which is an oscillating drive. Okay? And this oscillating drive will have both amplitude, frequency, and the phase of this particular drive. That will control my qubit rotations for this qubit. And this can come from your laptops. Okay? So you can design your pulses, write a code, and that will send this pulse to a dilution fridge, which is sitting somewhere in IBM's lab. And that, if you want to apply pi pulse, you can do that by writing a code from here. Okay? So that's exactly how you do these. Again, I'm not going into details of what is the strength of this drive. You can derive this again, do a simple circuit theory. Given a particular voltage, there is some capacitive coupling to the circuit over there. You can calculate how much voltage will be at this node. So it is controlled by this input capacitance that is used to couple your system. Okay? If this, ideally you would want this capacitance to be as big as possible for good control, but the more good capacitive coupling you have, the noise will also go into the system. Okay? So that's some trade-off that people have to do in order to figure out. That's kind of engineering one has to do to figure out how much this capacitor should be. Okay? So I'm not going into all those details, but this is essential idea of controlling your qubits from your circuits in circuit fashion. Okay? Similarly, you can imagine a flux drive also. Okay? So there could be some currents that you can send which will generate fluxes, and you can control qubits with flux as well. Okay. All right. Maybe in last 5 minutes I will take more to give you an idea of how to now do 2 qubit gates. So this is single qubit rotations. Right? So these are the lines in this architecture which actually are controlled by some electronics which you control by your laptops. Okay? So these resonator are the lines for you can see all these blue lines are connected to each of these red things. Red things are the qubits, and each of these blue lines are those microwave lines that controls applied oscillating voltage to each of these qubits. Okay? Apart from that, you see also green lines. These are connections between 2 qubits, and these are there for being able to do 2 qubit operations. Okay? So to create an entangling gate between the qubits, and there the idea is again. Let me first talk just quickly here. The idea there is, how do I create interactions between 2 qubits? Well, we can copy this single qubit gate, replace this voltage by the second qubit. Okay? Then the charge on this second qubit will control the charge, will talk to the charge on the other qubit, and you can generate an NN coupling between 2 sides by a capacitor. For example, this circuit over here will generate a term of the form NN. N1 on 1 will talk to the charge on the other circuit. Okay? So that's the type of interaction one will generate. Once we have that kind of interaction, you can again convert from this N language to N is just like a field, as I just mentioned, a transverse field. So it can give rise to sigma-sigma type of coupling, a transverse field type of coupling. So transitions in one will cause transitions in the other. So it creates a flip-flop type of transitions. So one qubit makes a transition from 0 to 1. That generates a field for the other one. It causes transition into 1, 0. So you can create a swap kind of operation. So a transition from 0 to 1 will cause 1 to 0 kind of transitions. Okay? So that generates a swap kind of gates. So qubits can swap. How much swapping happens, that depends on how long you keep this capacitor on between the 2 circuits. Okay? That generates how much swapping of the circuit can happen. Once you have this swap operation, I might have a picture here. Yes, this one. It turns out, as I mentioned, there are these circuit identities. So the C0 gate can be itself broken down into single qubit rotations. This we can do by applying pulses to each qubit and the combination of the swap gates. Okay, so this is a circuit identity that's known. So then you can generate C0 gate, for example, by combining these swapping operations with single qubit manipulations. Okay, and once you have these 2 things, you can generate a universal quantum computer. So that's the idea of 2 qubit manipulations. Last but not the least, we need to perform measurements on these qubits. And for that particular performance, do a measurement, the technique that's used is famously known as this dispersive readout. Okay? So the basic idea is you want to read this state without, again, imposing a lot of external noise in the system. Okay? And for doing that, what one does is, the essential idea is this is your qubit that you wanted to read. You again capacitively couple this system to now a linear LC oscillator, not the harmonic, not the anharmonic oscillator, but the harmonic oscillator. Okay. Without going into too much details of it, once you create this type of coupling, what happens is the frequency of this, what is the resonant frequency of this this LC circuit, even when it is widely detuned from the qubit gap. In this case, if they are exactly tuned with each other, they start talking to each other, right? So you detune them, and that's the so-called dispersive regime. But even in this detuned regime, depending on whether this qubit was pointing up or down, the resonance frequency changes of this qubit. Okay? And this frequency you can just measure by classically doing like a sort of an resonance experiment. You send in some microwave and see how much gets reflected. You can measure the frequency of this LC oscillator. By noting this where the frequency is, you can read out the state whether it's 0 or 1. Okay? That's the essential idea. And again, you can work out the math of this particular problem also. It's the famous so-called Jaynes-Cumming Hamiltonian that one generates. So roughly speaking, you can see this very quickly actually. So here's the two charges. Again, with the capacitor, they'll generate a term like NR, NC. Where NR is the charge on this resonator, NC is the charge on the qubit. So they generate an NN type of term again. And each of these N's, for the resonator, I can write them as A plus A dagger. It's a full linear resonator. So I need to keep, and I don't want to restrict the dynamics to just bottom two levels. So then I have to keep all the levels. So that's A plus A dagger. NC, I can just replace by the sigma Y. That's the charge on this capacitor. So that generates, sigma can be broken down again in sigma minus and sigma plus kind of terms. And that generates term of the following, again, like kind of flip-flop like terms in the leading order, which is A dagger combines with sigma minus, A combines with sigma plus. So you create a particle in the oscillator and flip, that creates a flip in the qubit. Okay? So that type of flip-flop terms are generated. And this is the famous Hamiltonian, which is known as Jaynes-Cumming Hamiltonian. Okay? So this capacitive coupling, this allows me to read. And if you solve this again in the leading order perturbation theory, probably in the interest of time, I will not go exactly in there. But if you solve it in leading order perturbation theory, the effect of it is the resonator frequency becomes a function of sigma z. Okay? So depending on whether the state was up or down, the resonance frequency shifts positive or negative for this resonator. And that shift is what exactly you measure by doing some simple resonator sort of like a microwave experiment. Just measure the frequency. Depending on where the resonance frequency shifts, that shift is given, you can measure it, as long as that shift is much greater than the spread of these levels. Okay? Spread comes because there is always interaction with the environment. So if that happens, then you can see this. And this is the technique that's used to perform the measurement. The same lines which are used to control, you can use them to read those qubits. Okay. So with this, I think, I hope you have an idea of at least how do you create such, do manipulations and create, read out such circuits and create couplings. The main advantage is all this electrical, very nice electrical control that's present for this particular circuit. Okay. That's why it's used a lot. Yeah, and the main challenges of the field are really errors, as has already been pointed out. There are various sources of errors in this case. So for example, this is my transpon, a single transpon coupled with an LC oscillator for readout purposes. It is coupled with external drives for control purposes. The material itself has defects that's living in there. All these couplings creeps in noise in the system. And the whole name of the game is how do you actually make it least sensitive to noise, still maintain the controllability. And here's sort of like a Moore's law for superconductor base, where about 1900, late 1990s, there was first qubit that was whether the circuits behave like quantum mechanical objects were shown. But a way to characterize the noise is really how much time you have such that this coherent evolution still happens, which is characterized by so-called T1, T2 times in these systems. And this is a plot of how does this T1 time changes over the years via various circuit techniques. Okay, and here's the transmon. As you can see, this was a major discovery that happened, which increased the times quite a bit from the computation time for which you can operate this circuit fully quantum mechanically, right? That time can be increased, and currently this is a good reference if you want to look at, this is where the current state of art is for such qubits, which can be of the order of about 10 power 3 seconds, 10 power 3 microseconds, right, in these systems. Okay, So that's where the status is, and just as last slide, two experiments that have been done recently utilizing these circuits. Two main results that have been shown are in the first Google experiment, where they actually generated one of those patterns, one of those probability patterns, specifically designed for quantum machines. Okay? If you can generate that particular pattern, what they showed was they were able to generate a pattern close to that what quantum mechanical, well, by close actually just tiny bit closer to quantum mechanical pattern. But if you want to generate that with a classical machine, it would take them like 10,000s of years. So that was the result that they showed. Again, that is not in itself usable because that pattern was not useful for anything. But that at least shows in principle there is this machine which can generate now a new kind of patterns much more faster than the classical machine. And very recently, IBM showed this result where they would actually show a utility function of this. So what they calculated was the average magnetization of a transverse Ising field model, which is essentially like a very simple model which has this sort of quantum mechanical difficulties built into it. And what they were able to show was using their so-called few hundred qubits machine, they were able to calculate the magnetization of such transverse Ising field models, which if you want to calculate classically, you cannot do those calculations. Okay? So that shows that for particularly doing these quantum material mechanical situations, these machines are getting close to showing at least some proof of principle advantage. And the main challenge is, can we scale this up to large scale systems? And that's what people are working on. Okay? So I hope that gives you a rough overview, and thank you for staying late. Sorry for surpassing a little time.